Hello everyone, in this video we're going to discuss gravitational potential energy. This is really crucial for energy problems, so let's get started. So the gravitational potential energy is equal to the mass times gravity times the height. So let's say we have a little situation over here where we have like the ground, or let's draw this lower. Let's say we have the ground right here, and if a ball was right here on the ground and we took this to be height equals 0, then this would have a 0 potential energy. But if the ball was up here, now it has some height, and so there would be some potential energy here. And if we had a ball below the ground, then it would have a negative potential energy. So this would be a positive potential energy. And so the thing with energy is it all depends on what you call your reference state. So if we said a new reference was right here and we called this reference height equals 0, or our potential energy here would now be 0, and these would both be negative potential energies. So depending on where you call your reference, it'll change the value. So it's important that you pick a reference that makes the question the most easy, and we'll talk about that later. And so a note on the units. For potential energy, we have kilograms, and then gravity is meters per second squared times the height, which is meters. So this is kilograms meters squared per second squared, which equals a joule. So this is indeed a unit of energy, just like kinetic energy or work. And so some other potential energies you might see is like a spring potential energy, which equals this equation, or you might see like gravitational, as in planetary potential energy, which can be described as this formula. So we'll talk about these in later units of physics. This will be talked about in Unit 7, and this will be talked about in Unit 6. So we won't discuss these right now, but these will be different potential energies you might see, and we'll cover those later. Alright, so let's do an example for gravitational potential energy here. So we have Bob, who is 68 kilograms, rides a water slide as shown below. So he starts at point 1, up here at 50 meters. He travels down, back up, and then all the way down. So we just want to figure out what is his potential energy along this path. So we want to know, in this first part, what is Bob's potential energy at point 1 relative to point 4? So when it says relative to point 4, we're going to make point 4 the reference point where the potential energy equals 0. So that means we can base our height off this reference point at point 4. So we know that our height now is just going to be this 50 meters, because this 50 meters is from this bottom reference point. So we know our U potential energy is just mass times gravity times height. So the mass is 68. That was not a 6 or an 8. The mass is 68 times gravity, which is 9.8. And so the height, we would use 50 meters. So if we plug those in, we'd get a potential energy of 33,320 joules. Okay, so what is Bob's potential energy at point 1 relative to point 2? So now, the mass and gravity aren't going to change for any of these, because he's not changing his mass, and the gravity is always constant. But now we have point 1 relative to point 2. Now note that he's still going to have the same, he's still, in the same position, but this time we're calling this the reference point, which means that we need to find this height, and we'll call this height B for question B. So height B is going to be equal to this total height minus the height of this at point 2. So it'll be 50 minus 25, and that'll give us 25 meters, because he's 25 meters above the reference point. So now we can use the same equation we just used and say the mass times gravity times this height from the reference point, which is 25 meters, equals 16660. Okay. So that shows that even though they're in the same position, he can have different potential energies because the reference is different. And so let's do another one. So he's at point 2 now, but we want to know the potential energy at point 2 relative to point 3. So now we're making point 3 the reference. So we need to know this height to get from point 2 to point 3, right? So if we want height, say c, then we can do the final, the initial height that they're at minus the reference height. So it'll be 25 meters minus the 35 meters, which is a negative 10 meters, because he's 10 meters below the reference point. And so when we go to plug in our equation here, we'll still have mass times gravity. And now for the height, we're going to plug in a negative 10 meters. And so this potential energy is actually going to be a negative potential energy. And basically all this negative means is it's below whatever we call the reference. And so we'll see, why is it that we can just call the reference anything, and how is that not going to mess up all the further calculations? So let's see this in part D. So we have, what is Bob's change in potential energy as he travels from point 1 to point 2? So in this case, it doesn't tell us what reference to use. It just says we want the change in energy. So we can find this potential energy at point 1 and 2 using any reference, as long as we use the same reference when we calculate both of them. So in this case, it makes the most sense to use point 4 as the reference, because it's at 0 meters off the ground. So it'll make all the calculations much simpler, and we can just use these values that we're given, right? So if we want to find the change in potential energy from point 1 to point 2, if we want to find the change in gravitational energy, we can simply find the gravitation at the final point, point 2, minus the gravitational potential energy at the initial point. And so this will equal the mass times gravity, the height initial minus the height final. So if we go ahead and plug this in, we would have the 68 times 9.8. And so the height initial, or it should be actually, sorry, it should be height final minus height initial, because it's potential energy final. Yeah. Okay. So we have the final height minus the initial height. So the final height here is going to be 0.2, because that's his final height he gets to, is 25, and he starts at a higher point of 50. And so if we were to plug this in, we would get a negative 16660 joules. So that's the change in potential energy. So even if we were to choose, let's for example just choose 0.2 as the reference. Right? If we choose 0.2 as the reference, we want to use this height b again. So we already know Bob's potential energy at point 1 relative to point 2, which is this energy right here. And so now, if we want to do the change in potential energy using point 2, we know the final is going to be 0 because we set this reference to at point 2. So if the reference is at one of the points, we can automatically set that to 0. And we minus the initial, which is initial from the reference point. And since we already did 1 relative to 2, we're just going to subtract that 1660 joules. And notice we get the same answer as we got when we chose the initial point as the ground. So changing the reference point will only change each individual potential energy, but the change in energy is going to be the same. So now let's do this last problem here. So how much work does gravity do on Bob as he travels from point 1 to point 2? So if we wanted to solve this how we know how work, like using our normal work equation, equals force times distance, we can do this because the force that's acting on Bob by gravity is just Fg times the distance. And notice Fg equals mg. So we just get this mg times distance, which in this case is the height from point 1 to point 2. And so the work just equals the mg times the height, which we know it's still going to be 68, 9.8, and the height from point 1 to point 2, as we found earlier, was 25. So we will get 1660 joules. And notice this work equals the negative change in this gravitational potential energy, because we had a negative here, so the work was the negative change. And what will be easier to think about in most cases is that the change in gravitational potential energy is the amount of work that's lost in the system. So that's the big idea. The one other thing about potential energy here that I should have mentioned is that when we're doing potential energy, we have to define our system with two separate objects. So our system here was, let's use this highlighter, was Bob, but then Bob also has to be relative to something else. And in this case, Bob is relative to the Earth. So the Earth is the other part of the system. So it's a Bob Earth system. So if there's nothing else in anything else in the system, it can't have potential energy. So if you here define the system as like the object and the Earth, it's basically saying that they both need to be included so that you can relate the energies of the two. Alright, so that's all I got for potential energy. Make sure you stick around for next episode where we'll talk about conservation of energy, which is super important and uses and combines the kinetic, potential energy, and work. So alright, leave your comments down below, and thanks for watching.